and data analysis to guide you as you carry out your research project. Learn from the PhilSciHub team of research scientists and some invited subject matter experts. PhilSciHub Research University will be your personal coach through every stage of your research project, from ideation to final assessment. And the best part? It's absolutely free. Visit us at philscihub.com and be part of this learning journey. Let's learn and succeed together here at PhilSciHub Research University. Welcome to PhilSciHub Research University, your ultimate guide on your next research project. We will lay down the best practices in research ideation, literature review, experimental design, and data analysis to guide you as you carry out your research project. Learn from the PhilSciHub team of research scientists and some invited subject matter experts. PhilSciHub Research University will be your personal coach through every stage of your research project, from ideation to final assessment. And the best part? It's absolutely free. Visit us at philscihub.com and be part of this learning journey. Let's learn and succeed together here at PhilSciHub Research University.
Mabuhay! Welcome to the Filipino Science Hub. Thank you for your continued support to this online platform. To our new participants, thank you for checking us out today, and we would like to officially welcome you to the PhilSciHub family. Before we start the webinar, I would like to share some house rules in order to facilitate a smooth session. For our Zoom participants, we would appreciate it if you could turn your audio and video cameras off during the webinar. If you have questions or comments, feel free to type them on our Zoom chat box or YouTube live comments, and we will try to accommodate as much questions as possible. After the talk, we will have a 30-minute Q&A where the Zoom participants will have the opportunity to ask their questions live. For those who would like to receive a certificate of participation, a Google form link will be posted on our Zoom chat box, YouTube live comments, and YouTube video description towards the end of the webinar. Again, welcome to all our Zoom participants and YouTube live viewers. For those who are new and may not be familiar with who we are and what we do, allow me to share our mission and vision in the next few minutes. Filipino Science Hub is an online platform founded by our CEO, Filipino scientist, Dr. Jeffrey Camacho back in 2012. Currently, we are a registered nonprofit organization based in Houston, Texas, United States. Our mission is to promote STEM education and the culture of research among students and teachers in the Philippines and abroad. Our current global leadership team is comprised of volunteer Filipino scientists, seasoned STEM educators, and business executives across the globe. Our vision is to see a technology and innovation-driven Philippines, and we believe that this can be achieved by creating a new generation of well-rounded Filipino STEM enthusiasts. The vision is being carried out via our two major programs, the PhilSciHub Ed program and the PhilSciHub Research University. Through PhilSciHub Ed, we are able to empower and support our teachers by strengthening STEM fundamentals education. We believe that this is important because the more equipped our STEM educators are, the more they can inspire students to pursue a career in science, technology, engineering, and mathematics. The other major program that drives our vision forward is PhilSciHub Research University. This is where we provide tools for fundamentals of research and bring practicing scientists closer to the educational sector. Our official website is www.philscihub.com. This is where you can access all our materials such as webinars, tutorials, modules, virtual lab, and features, all of which are free. We are also present in several social media platforms, so follow us wherever you are most active on to get updated with our web events. Again, thank you for being with us this morning. To officially start our webinar, I would like to turn the virtual floor over to our host today.
Okay, magandang umaga po sa inyong lahat. Maraming salamat po sa pagsama na naman ninyo sa amin ngayong araw ng Sabado. So today we will have the fourth and the final installment of the Filipino Science Hub and Hub's collaboration with the Institute of Mathematical Sciences and Physics at the University of the Philippines, Los Baños. So ito po ang ating Physics Month. Dapat po nung October, unfortunately po dahil sa bagyo, medyo umawas tayo, naging Physics Months tayo ngayon. So umabot tayo ng November. But we're hoping po that everyone is safe after po ng bagyo dyan sa Pilipinas. Pero before po tayo pumunta talaga sa ating talk, we would like to call on the director of the Institute of Mathematical Sciences and Physics of the University of the Philippines at Los Baños. So my Math 17 professor, Professor Editha Jose.
Thank you so much, Doc Jeff. So, yeah, sabi nga ni Doc Jeff, dapat last week natin nag-conclude yung ating Physics Month, a collaboration between the IMSP and PhilSciHub. So, sabi ko kay Jeff ay mag-live talk ako ngayon dahil hindi ako nakapag-record, but also because this is the last installment of our webinar series. So let me just personally thank all the people behind this celebration of Physics Month. So on behalf of the Institute of Mathematical Sciences and Physics, UP Los Baños, I would like to welcome you all to the conclusion of this month-long series of webinars to celebrate October plus November as Physics Months. So I am really thankful to the whole organization of the Filipino Science Hub, headed by my former student, Dr. Jeffrey Bungkuin, for collaborating with us in our common pursuit to uplift the quality of STEM education and research in the country, and at the same time promote the wonders and power of physics. So I would like to mention my colleagues from the IMSP who wholeheartedly shared their time and expertise in the past month. So first, we have Dr. Alan Alinea, who opened the series with his talk about walking through the universe. The second week saw the group of physics educators who prepared presentations on DIY physics experiments. So it seems we will have a part 2 of that blockbuster session. Our third speaker was Dr. Anthony Alan Villanueva, so a passionate theoretical physicist who not only communicated about quantum physics, but shared valuable insights about his career in research and academia. And for today, of course, we will hear about computational materials physics from Dr. Darwin Putungan. So I truly appreciate and thank our speakers for this Physics Month. So to all participants either in Zoom or YouTube, so thank you for your participation, and we hope to see you in our future events with PhilSciHub. So as I am telling from day one, this is just the beginning of PhilSciHub cross IMSP collabs. So watch out for more.
Ayan, maraming. No, so kompleto naman, ma'am. Before naging medyo choppy yung connection, but again sakto po. We would like to thank po again like the Institute of Mathematics.
Unstable daw kasi yung internet.
Opo. So we would like to thank the Institute of Mathematical Sciences and Physics for this collaboration. So gaya nga po ng sinabi namin, nagsisimula pa lang po tayo. Medyo mahaba-haba po ang pagsasamahan ng IMSP and Filipino Science Hub. So at this point, I would like to grab the opportunity and the honor to introduce today's speaker. So our speaker for today is Dr. Darwin B. Putungan. So si Professor Putungan po, he finished his bachelor's degree in physics at the University of the Philippines, Los Baños, cum laude. He then went on and pursued he earned his master's degree in physics at the University of the Philippines, Diliman. And then after that, he took up and earned his Doctor of Philosophy and Physics degree from the National Taiwan University. And at present, he is a professor of physics at the Institute of Mathematical Sciences and Physics at UP Los Baños. And his research work focuses on density functional theory, based calculations and kinetic Monte Carlo simulations, mainly in the field of 2D materials for energy conversion and storage. And so with that, it is my great honor and pleasure to introduce to you or to bring you Dr. Darwin Putungan. Sir Darwin, take it away.
Okay. Hello. Thank you, Dr. Jeff, for the nice introduction. And also, I would like to thank PhilSciHub and IMSP for giving me this opportunity to share to you my research works in 2D materials. So let me first share my screen. Okay, so I hope you can see my screen. Okay, so for today, I'll be sharing to you the physics and applications of 2D materials through this talk titled 2D or not 2D? That is the question. Actually, this title is a pun on a very famous line or phrase in a play by Shakespeare, that is Hamlet. Okay. Okay, so that phrase is to be or not to be. And this represents Hamlet's dilemma between life and death. So it sounds like 2D or not 2D. If you read it fast, it's 2D or not 2D, something like that. But the idea is that materials dimensionality is important in many applications. So whenever we want to let's say, use a material for a specific application, then we can also contemplate on the material's dimensionality, and we can ask ourselves, 2D or not 2D, or use 2D or not 2D materials. Okay, so let me introduce first what basically a 2D material is. Okay, so the material that we usually know are what we call 3D materials. These are also called bulk materials. Okay, so let's say you're an electron, and you enter into this material here, which is a 3D material. And if you try to measure the dimension of this material, this 3D material, along the X, Y, and Z axis, then you'll see that effectively the dimensions of this material is effectively infinite. Okay, if you're the size of an electron. That's what we mean by a 3D material. So there's an effective 3D periodicity in the material. Like it's an infinite repetition of the constituent atoms or constituent molecules, something like that. Now, for a 2D material, on the right-hand side, what happens is that if you cut the material along one of the axes, let's say you cut the periodicity along the y-axis, like here. Okay, so it still has an infinite periodicity along the z and along the x directions, but along the y direction, it's now really thin. So the dimension now along the y-axis is fine. So if you're an electron and you enter this material, you'll see that along the y direction, it's like you are trapped, okay, between two walls. Okay, so it's like you're restricted. So your movement is restricted along the y-axis. Okay, so in essence, so a 2D material is a material wherein there's a reduced dimensionality in one axis. So it can be along the X, the Y, or the Z, it doesn't matter, as long as it's along one axis. Okay, so your electrons, okay, so let's say you're an electron, your movement will be restricted along one of those directions. Okay, so that is a 2D material. And so let's now have some survey of those common 2D materials. And one of the most famous 2D materials is graphene. Okay, graphene is actually the 2D version of a 3D bulk material, which is called graphite. Okay, this is how graphite looks like. And its structure is given on the right-hand side. So the structure is, it's a hexagonal. It's a network of carbon atoms in a hexagonal fashion, and then it's arranged in a layered structure. And as a 3D material, graphite is quite a good conductor of electricity. Okay, although it's hard, but its hardness is not enough, and you cannot utilize it as a structural material. So that's the 3D version of the material. Okay, so we call it graphite. Okay, now, since the structure is a layered structure, you can think of it as if you have many sheets of carbon atoms that are arranged like a paper pad. Okay, so each of the sheets are arranged in layers. Now, you can actually shed off one layer. Okay, and if you do that, you'll have the 2D version of graphite, which is graphene. And it was Andre Geim who first isolated graphene. So he won the 2010 Nobel Prize in Physics because of that. And the method that he used was very simple. It's what we now call Scotch tape method. So what he did was basically he just, used a Scotch tape, then put it on top of graphite, then try to scratch it or peel off the layers until he found graphene. Okay, so it's a very simple method. And because of that, he won the Nobel Prize in Physics. But it's not just because he was able to use the Scotch tape method. That's not the only reason why he won the 2010 Nobel Prize. The idea is that he actually revolutionized the physics of 2D materials because he's the first one to isolate a 2D material, and that is graphene. And after this, many other scientists tried to isolate many other 2D materials, and that started the plethora of so many 2D materials that we know today. Okay, and just for your information, Andre Geim also won the Ig Nobel Prize in 2000. Okay, so the Ig Nobel Prize is actually it's a parody of the Nobel Prize. So what scientists do here is they perform experiments that are a little, I would say, a little funny. Okay, experiments that you would not normally do in a laboratory. So what Geim did was he levitated a frog in the presence of a magnetic field. So that was his winning experiment. And up to now, up to date, he's the only person to win both the Nobel Prize in Physics and an Ig Nobel Prize. Okay, well, that's a trivia. And so this is graphene. So it's a single layer of graphite. Okay, so it's transparent, unlike graphite that is like a charcoal. Okay, on the right-hand side is the structure of graphene. So it's a single layer of carbon atoms. Okay, this structure is called the honeycomb structure. So as you can see, if you look at on the top, then you'll see that it's a hexagonal network of carbon atoms. And so you can see that along, let's say, the z-axis. Okay, so let's say this direction is X, and then you have Y, and out of the screen, that's your z-axis. So the dimension along the z-axis is just a single layer. So it's an atom thick, one carbon atom thick. Okay, so it's a truly 2D material. And so just because we trimmed graphite into its 2D version, which is graphene, a plethora of new properties emerged. Okay, so before, when we have graphite, it's a good conductor of electricity, but not that good enough. Okay, but for graphene, it's an excellent conductor of electricity, much better than graphite. And also, graphene was found to be the strongest material ever. Okay, and it's around 40 times stronger than diamond, then 300 times stronger than steel. Okay, so as you can see, what happened here was from the same material. So the 3D version, you have graphite. Then once you convert it, or you were able to extract a 2D version of the material, in this case, graphene, the properties become so exotic. It's very different from its bulk counterpart. Okay, another example would be MOS2, or molybdenum disulfide. Molybdenum disulfide is different because it's not a single atom thick. Okay, the structure is the same. So you have a layered structure. So this is one layer, then you have another layer here, but it's 3 atom thick. Okay, so MOS2 belongs to a class of materials called transition metal dichalcogenates. So you have one transition metal, you have molybdenum here, and then you have two chalcogen atoms. So in this case, you have sulfur. So sulfur layer on the top and sulfur layer at the bottom. So you have a sandwich chalcogen, transition metal, chalcogen structure here. So for the bulk structure of MOS2, this is how it looks like. This is the structure. And on the right-hand side, okay, what we have here is what we call a bond structure. So it tells you the electronic property of the material. So it tells you, or it can tell you whether your material is a metal, a semiconductor, or an insulator. And that would depend on this blue line here and the green line here. Okay, so the blue line here is what we call the valence bond maximum. And then the green line here is what we call the conduction band minimum. So as you can see, there's a gap. Okay, so the y-axis here is energy. So we can see here that there's an energy gap between the green line and the blue line. If there's a gap, then the material is a semiconductor, especially if that gap is not that high. Okay, so in this case, that's 1.2 electron volts. Okay, but what's noticeable here is that, okay, for the blue line, its maximum is actually here, but for the green line, it's around here. Okay, and so there is no direct, okay, there's no direct correspondence between the valence band maximum point here and the conduction band minimum point here. So they are not, there's no direct correspondence. And if that's the case, then we call the semiconductor an indirect gap semiconductor. Now, if your semiconductor is an indirect gap semiconductor, that means that it's not a good material for photovoltaic applications. So what do we mean by a photovoltaic device? Okay, those are the devices that we use in solar cells. Okay, so the idea is in a solar cell. So if you use, let's say, a semiconductor material like MOSO, for instance, and if it's an indirect gap semiconductor, what happens is that if light strikes the material, then electrons would transition from your valence bond to the conduction bond. That's what usually happens. And then you collect the electrons and you have a flow of electrons and you have a current. But for an indirect gap semiconductor, what happens is that your electrons cannot transition directly from the valence band maximum to the conduction band minimum because there's no direct correspondence between the 2 points. So what the electron will do is it will transition first, okay, from this point to a temporary state, okay, and that means that it needs to transfer momentum, okay, and once it transitions from here to here, okay, once it has now a direct correspondence to your conduction band maximum or a minimum, that's when it can jump to that state. So in short, what happens is that your electron needs to go to another state first before it can transition to your conduction band maximum. And that implies loss of energy, or it's inefficient. It's an inefficient process. So that's what is happening for a bulk 3D MOS2. Okay, that's why it's not good for photovoltaic device applications. However, if you peel off one layer, and so you now have a single layer MOS2, which is a 2D material. Okay, that's the 2D version of a bulk MOS2. What happens in its bond structure is that you now have a direct gap semiconductor. So there's now a direct correspondence between your valence band maximum and conduction band minimum. And if that's the case, then this material is a very good material for photovoltaic device applications. So as you can see, the 2D version of this material is very different from its 3D version. Okay, now you might ask, why is that so? So why is the 3D version of the material very different from its 2D version? Okay, so what exactly is happening here? Okay, the key idea behind that difference in properties is a phenomenon called the quantum confinement effect. So, in simple words, quantum confinement effect is, it's like trapping your electrons in a quantum well, one-dimensional quantum well, because you are cutting your material in just one dimension. Okay, so in this case, like what is shown here in the figure on the left, so if you restrict your electrons along the y direction, meaning to say you cut the periodicity along the y direction, then it's like you're trapping your electrons in a quantum well along the y direction. So it's like this figure here at the bottom. Okay, so your electrons will just be able to have a movement, okay, or exhibit motion along this or in this region, but it cannot go on the other side, on either side. Okay, so that is a quantum well. Okay, there's a large barrier, okay, on the side, and this is the dimension of that that well, which can also be correlated to the finite size of your material along the y direction. Now, if that's the case, if your electrons are trapped in a quantum well, okay, so in quantum mechanics, we can actually solve that system using a model called particle in a box, okay? And if you solve the Schrödinger equation, okay, using that, that particle in a box potential, then we'll see that there are changes in the electron's behavior or properties in this region here. And we can see that, or we will see that their energies are discrete. Okay, so meaning to say it's like the rung of a ladder, or rungs of a ladder. You can only be on the first rung or the second rung. You cannot be on 1.5 rung. Okay, so the steps are discrete. So that's also what happens here in this region. And it turned out that that change in the property of the electrons, okay, the discretization of their energy, results to a plethora of new properties for that material. So that's the reason why the properties possessed by a 2D material is very different from that of its 3D counterpart. Okay, but that's just the baseline. Okay, of course, the general property, okay, or overall properties of a 2D material would depend on the constituent atoms. Okay, so what I'm saying is that the quantum confinement effect gives us the baseline. Okay, it's the baseline for the changes in the properties of a 2D material. But whether a certain 2D material will possess, let's say, a good property for photovoltaics, or very good property for catalysis, or something else, that would depend on the constituent atoms of the material. That is because, okay, we can categorize our 2D material, okay, in terms of the strength of the charge transfer between the constituent atoms. Okay, so we could have different bondings, okay, between the constituent atoms of 2D materials. So we could have covalent bonding. Then on the other end, we have the ionic bonding. And there's in between. There are something like in between covalent and ionic bonding. Okay, so there are many materials that belong to each of these categories. And for the extreme covalent case, that's where we have graphene. So graphene is a covalent 2D material. Okay, similarly, we have silicene, germanium, and phosphorine. Okay, silicene is the 2D version of silicon. Okay, so scientists now were able to isolate 2D versions of silicon also, and they call it silicene. Germanium is the 2D version of germanium. Phosphorine is the 2D version of phosphorus. Okay, and these materials are covalent 2D materials. Okay, and as we go along this this direction towards the ionic bonding, so you have a lesser covalently bonded materials like boron nitride, silicon carbide. Then we have the metal chalcogenides and the PMDs, or transition metal chalcogenides. And lastly, for the ionic 2D materials, we have the metal halides. Okay, now it turned out that depending on the bonding mechanism between the constituent atoms, the applications will also varies depending on that bonding. And for those covalently bonded 2D materials, in most cases, they are good for electronics applications because most of these materials are semiconductors. So they're good in MOS applications like transistors, metal oxide transistors, optoelectronic applications, things like that. And those that are on the other side, close to the ionic bonded to the materials, they are good for catalytic applications, meaning to say you can use these materials as catalysts in certain applications. Okay, but for me, one of the most interesting 2D materials for me are the TMDs. Okay, MOS2, WS2, tungsten diselenide, vanadium ditelluride. And the reason for this is because most of the materials in this category are actually good for both electronics and catalytic applications. That's why they are very interesting. It's like they are one of the most versatile 2D materials. Okay, and so most of my research works focus on TMDs, on 2D TMDs. Okay, now I'm a computational material physicist, and I do my research by modeling and simulation, by doing modeling and simulation of materials. Okay, and so I would like to introduce or to share why do we need to do computational physics in general. And I would say that computational physics is a new way of doing physics, because traditionally there are two ways of doing physics. So we do experiments and we do theory. Okay, theory is we can describe it as understanding of reality. So here you write equations, describe and understand the reality. Experiments, these are observations of reality. So you do experiments to observe what's the trend or what's the relationship between two quantities, something like that. Okay, so these are the traditional ways of doing physics. So we do theory, we do experiments. Now with the advent of modern technology, with the rise of computers, okay, another way of doing physics emerged, and that is computational physics. And usually we call that simulations. Okay, and sometimes we interchange the terms modeling, simulation. Okay, but in actuality, those two are different. Okay, modeling is different from simulations. Okay, so let me give you an example. So, okay, one of the uses of computational physics is to supplement and validate experimental results. Okay, like for instance, if we have a theory, let's say condensed matter theory, we have a theory on solids. Okay, how solids vibrate. Okay, and so those vibrations can be probed by experiments. Maybe you can use some spectroscopy experiments, okay, to obtain those vibrational modes. Okay, now how are we going to do that? Okay, to get the vibrational modes using computational physics. Okay, the first thing that we need to do is to model the material. Okay, so how are we going to model the material? So the purpose, okay, the purpose of using a model or doing modeling is to better understand the theory or to make it more intuitive. Meaning to say, it will make you visualize the theory better. Okay, like for instance, okay, I can model a vibrating solid by, let's say, okay, using some solid spheres and then connect them by springs. Okay, and then if you try to pull one side of the material, that will vibrate, right? So that's a model of a vibrating solid. Spheres connected by springs. Okay, and what you can do is, okay, let's solve the equations that describe that model. Okay, so you write some differential equations, then you turn it into an algorithm, And later on, you turn it into a program, and then you can do the simulation. And from that, you can obtain the vibrational modes of your material. And what you can do is to compare to the experimental results, and you do validation. So if your results are very close to the experimental results, then that means that your model is accurate. If not, then you can tweak your model. You can add something else, like I need to tighten the spring, or I need to loosen the spring, things like that. So in short, that's a way of understanding better the theory. And at the same time, you can use that to validate experimental results. That's one important use of computational physics. Now, another important use of computational physics is that sometimes there are phenomena or certain, let's say, processes wherein there's no way for you to do an experiment, right? And the only way for you to understand that phenomenon is to do simulations. And one of the examples that I would like to share to you is that news before. I'm not sure if you have heard of it. It's about diamond rain, okay, on Saturn and Jupiter. Scientists predicted that in Saturn and Jupiter, the rain is actually diamonds. So their atmosphere, okay, because the atmosphere is very dense and the situations and conditions there on Saturn and Jupiter are very appropriate for diamond to be stable. And that's what happens there. So it rains diamond in Jupiter and Saturn. And of course, you might ask, how did they know? Of course, they did not went to Saturn and Jupiter and try to collect diamonds, right? You won't be able to do that. So what scientists did here was to do simulations. And one of the methods that they did to predict whether diamond structurally is stable under conditions in or Saturn and Jupiter's atmosphere is by doing what's called density functional theory calculations. Okay, this is actually the method that I'm using in my research works. This is a quantum mechanical method. Okay, and so let me just briefly, briefly tell you what is density functional theory. Okay, so this equation here, okay, this H psi is equal to E psi. This is the many-body Schrödinger equation, and it was casted as an eigenvalue problem. Okay, so this psi here is the wave function. Okay, so we know that electrons exhibit wave-like properties. Okay, and Schrödinger's equation is a way of finding that wave function. And at the same time, you also want to find the corresponding energy. Okay, now the problem is that if your system is a large system consisting of many electrons, many protons, many neutrons, okay, your wave function would be written this way. So it contains all the coordinates of your electrons and all the coordinates of your nucleons. Okay, nucleons are the protons and neutrons. Okay, and so if you have a real material, let's say a real solid material, which contains many, many electrons, many, many nucleons, then effectively this many-body Schrödinger equation is unsolvable. Okay, because you have so many coordinates, parameters for your wave function. This is effectively unsolvable. So, okay, what the first step of simplifying this equation is to realize that the nucleons, the protons, and the neutrons are much heavier than the electrons. Okay, so a proton is around 1,800 times, okay, heavier than an electron. So one approximation that we can do is to think that, okay, since these protons and neutrons are so heavy, while the electrons are so light, so let's just make this assumption that the nucleons are just fixed in space, and let's just allow your electrons to move. Okay, so what happens here is that you remove this dependence on the coordinates of the nucleons or protons and neutrons and just fix them. Okay, and so what you have here would be just the coordinates of the electrons, because they are just the ones who are moving. Okay, that's the first approximation. So your wave function would now be just dependent on the coordinates of the electrons, because you can fix the coordinates of the protons and the neutrons. Okay, but still, that's not good enough because your electrons are interacting. Okay, and it's very difficult for an equation to be solved if you have coupled equations and if there are interactions between your particles. So the second simplification for this problem is, okay, let's remove the interactions between the electrons. Okay, let's pretend that they are not interacting and just let them interact. Okay, or let them just be influenced by what's called an effective potential. Okay, so essentially what the DFT guys did here was they removed the interaction, the actual interaction from the electrons, and put it in what's called an effective potential. Okay, and so with that, you remove the coupling between the electrons. And once you remove the coupling, then you can write a single one electron equation like this here. Okay, that is influenced by just this effective potential. So this is what we call the quantum equations. Okay, this is the basis of density functional theory. Okay, and to make it more intuitive, let me just show you this diagram. Okay, so in reality, the left-hand side here, okay, this is the difficult problem. This is the real difficult problem. You have interacting electrons, but let's say it has a charge density or electronic charge density, let's say N of R. Okay, so what they did was they converted it into a solvable problem wherein they remove the interactions of the electrons, okay, and put it in an effective potential, okay, and write the one electron equations that can be solved easily. Now, the important thing is that these two should have the same charge density N of R. That's why this method is called density functional theory, because you are basically making use of the electronic density. Okay, that means as long as these two has the same electronic density, then it's okay to convert this difficult problem into this solvable problem. That's the idea behind density functional theory. So with that, we don't need to solve that very complicated many-body Schrödinger equation. Instead, you just solve those simple quantum equations. So in short, density functional theory is a reformulation of the many-body Schrödinger equation for us to be able to solve it much easier. Okay, so this is another illustration of what the FT is. Okay, so again, so in a many-body perspective, this is what we have. So your ions are interacting with all of the electrons, and each of these electrons are interacting with each other. Okay, but in DFT perspective, you don't have this individual electrons. What you have is just the electron density. Okay, and you're not also concerned with each of the coordinates of the electrons. You're only concerned with the coordinate of the electron density. So it's like finding the center of mass, right? So here, you just find that one or three coordinates, x, y, and z, that describes the or represents your electron density, and that's it. You just need to interact with that. Okay, so that's essentially how DFT made that difficult problem easier. Okay, now let me just give you an example of how important the electronic charge density is. Okay, that DFT perspective. Now, the advantage is, okay, let's say you have a 100 atom platinum cluster. Okay, using the full wave function. Okay, how many variables do we need to put in? Okay, so 100 times 78. 78 is the atomic number of platinum, then times 3, because each of those electrons would have 3 coordinates, x, y, and z. You would have around 23,000 variables. Okay, that's too many for us to solve. Okay, but if you just use the electronic density, you only need 3 variables, x, y, and z. Okay, because your electronic density can only be represented by only 3 spatial variables. Okay, X, Y, and Z. So that's essentially the importance of density functional theory. That made the calculations much easier and computationally less expensive. Okay. Okay, now these are the questions that can be asked and can be answered by density functional theory calculations. So let's say you have, you want to predict, okay, if a certain material, or let's say a certain atom or molecule could exist, then you can use density functional theory. Okay, and there you could predict that, okay, if I combine these atoms, would it be a real material? You can predict that using density functional theory. And let's say you were able to construct, okay, a certain material. What are their properties? Is this material a semiconductor, a metal, or an insulator? Does it have catalytic properties, etc., etc.? You can also ask that question, and you can answer that using density functional theory. So that's the power of density functional theory in computational materials physics. Okay. Now, okay, another important note about doing simulations and calculations. Okay, many people might ask us, okay, why do you do simulations or calculations? Why not just buy devices or equipment and do experiments? Okay, now, the idea of doing simulations and calculations is for us to discover new materials and subsequently to produce new innovations. Okay, simulations and calculations fall under the basic or fundamental research category. Okay, and let us all remember that all innovations, discoveries, and things like that, they all start from basic research. Okay, so we need to first understand, okay, what's happening, or what's the properties of the material. Okay, once we predicted that, okay, then experimentalists can discover that, try to synthesize the material. And then once they were able to synthesize it, then the innovations start. And that's the importance of doing simulations or calculations. Okay, and also in doing simulations or calculations, we are doing what we can call computer experiments. It's like you're also doing an experiment, but not in a wet lab. Okay, it's on a computer. And there's also this term, materials genome. Okay, so this is a prediction of materials properties for specific applications solely using modeling and simulation. So it's similar to the human genome, right? The mapping of the complete genetic makeup of a human being. So you can also do that on materials. So what you can do is you probe the periodic table, okay? Then you try to combine elements and then predict if the 2D version of this material would exist. Are they stable, not stable? What are the structures? What are the properties? And you can make a database, okay, for those materials. And that's what we call materials genome. And many people are doing it right now. Okay, and actually there's a initiative by the National University of Singapore, and what they're doing right now is they're constructing what's called 2D materials encyclopedia. So they are predicting materials, okay, their 2D versions, and then they're trying to see if these materials are good for very specific applications, like for instance, hydrogen evolution reaction, water splitting, things like that. Okay, so like for instance, the potential application of this is, let's say you're a startup, you are creating a startup company. Let's say, yeah, I want to construct a device that I can use for producing hydrogen. Okay, and I want to utilize a 2D material. What you will do is you just search, okay, or browse through this encyclopedia, okay, 2D material for HER, and it will give you those 2D materials that could be utilized for the application that you want. So that's basically the goal of this encyclopedia. And of course, these are not yet complete. They are still predicting many more 2D materials. But this is a very good initiative for materials genome. Okay. Now, let me just share to you some of my research works, okay, in the field of energy conversion and storage. So what I will share to you are my works on metal ion batteries. Okay, so metal ion batteries are good and are needed, especially in storing harvested energy. Like for instance, if you have a solar cell panel or solar cell panels at your homes, then you need to store the energy that you harvested in a battery because it's not always sunny, right? I mean, at night, you won't be able to have current coming from your solar cell. So you can only utilize that energy if you stored it in a battery. And one of the commonly used batteries are the metal ion batteries. Okay, and the most popular in use right now are the LIBs or lithium ion batteries. And the figure here shows you a typical construction of a lithium ion battery. So you have an anode, you have a cathode, and then you have an electrolyte in between. And what happens here is that if you put a load somewhere here, then electrons would, okay, flow here, while the ions would migrate through the electrolyte and go to the cathode. Okay, and so the idea of using lithium-ion batteries is that you'll be able to store energy in chemical form, and you can utilize it in portable devices, just like nowadays, all of our smartphones are powered by lithium-ion batteries. Okay, and of course, the idea is to reduce our reliance on fossil fuels, because if you have working batteries, then you can utilize renewable energies, wind energy, solar energy, and then just store them in batteries for later use. So that's essentially the basic idea behind using lithium-ion batteries. But there's a problem in using lithium-ion batteries. Okay, if you look at this graph here, this tells you the composition of the Earth's crust. Okay, composition of the Earth's crust. The x-axis are the constituent elements of the Earth's crust. And you can see that lithium is actually at the bottom of this chart. Okay, that means the concentration of lithium on the Earth's crust is very small. Okay, it's very small. It's actually second to the last. And with that, if we continually use lithium-ion batteries, then that would mean in the future, it would cost very high, just like gold. Okay. And so the idea is, why not try other elements? Okay. So we might try to look somewhere here, the abundant elements on the Earth's crust. Okay. And so one of those elements that people are now looking at is sodium. Okay, sodium is very abundant. It sits right here. Okay. And so why not maybe construct a sodium ion battery instead of lithium ion battery? And that's actually what people are now doing. So they are now trying to see if sodium ion batteries are feasible. Okay, and if it could replace lithium-ion batteries. Okay, the advantages of sodium-ion batteries, that's very abundant. Okay, low cost. Actually, if you have an effective way and efficient way of separating sodium and chlorine from salt, then essentially you have an unlimited source of sodium. Right? All you need to do is to get salt, extract sodium, and there you have it. You have a sodium-ion battery. And in most cases, it's safer compared to lithium-ion batteries because for sodium-ion batteries, it's okay to use non-flammable electrolytes. The problem with lithium is mostly the electrolytes that we use are flammable, and that's the reason why lithium-ion batteries usually explode. Right? But there's one disadvantage in using sodium-ion batteries. The disadvantage is that sodium ions are much heavier compared to lithium ions. Okay, so its charge to weight ratio is lower compared to lithium. What's the implication of that? The implication is that for the same energy capacity of lithium-ion battery, okay, you need to construct a larger battery if you will use sodium. Okay, so that's the idea. So you cannot really use sodium-ion batteries in portable devices because you'll be using a larger pack or package for the battery. Okay, but that's the only disadvantage. Okay, I mean, if the application is not for mobile applications, let's say if the intended application is for fixed batteries, then sodium-ion batteries are very good alternatives, or a very good alternative to lithium-ion battery. Okay, and people are actually trying to do some analysis, cost analysis. Okay, and they are seeing that if you use sodium for sodium-ion batteries, then you can reduce the cost of construction by around 24%. Okay, so sodium-ion batteries are really cheaper than lithium-ion batteries. Okay, and this is what I'm talking about. So in the future, many cities could be converted or would be converted to what are called smart grid cities. Okay, wherein there are lots of like sensors that would change the power supply, things like that, overall the city, depending on the situation. Like if there's a power interruption, then it will activate its generators or it will activate its alternative energy resource that would power the city, okay, in case of emergencies. And for this type of cities, fixed batteries are very important. So this is where sodium-ion batteries could be very helpful. Okay, so now let me just share to you some metrics. Okay, okay, for computational physics, there are two important things that we want to look at. Okay, candidate electrodes for sodium-ion batteries. Now, the idea is that you cannot just simply replace lithium with sodium. Okay, because in most cases, the electrodes that are working for lithium do not work for sodium. So you also need to find the appropriate electrode materials for sodium-ion batteries. And these are the two important things that one could consider in searching for the appropriate electrode material. Okay, the first one is the metal ion binding energy, that's sodium binding energy, on that material should be high enough. Okay, so that it's possible for the material to have a high specific energy capacity. And second, the diffusion of sodium ion on the material, okay, should be as small as possible, because that diffusion energy barrier would imply or would give you an idea of how the ions would migrate on the surface of your electrode. And that would also give you an idea of how the charging and discharging of the battery would be efficient or not. So these two are the important metrics that we could calculate, okay, to predict if a certain material is good for sodium-ion battery or not. And so what we did was we tried to consider, okay, a 2D material called vanadium disulfide. Okay, so this material has two structural phases. So the first one here on the top, this is what we call the 1H, and at the bottom is the 1T phase. Okay, so as you can see, the coordination of the vanadium and sulfur atoms are different, right? Okay, both of these materials are metals. Okay, as you can see, there's no energy gap, right? And your band crosses this broken line here, which is what we call the Fermi level. Okay, so if that's the property of your bond structure, that means these materials are metallic, and that's good as anode materials for battery. Okay, you need metallic electronic structure for those applications. Okay, so these are appropriate for sodium-ion batteries. And so the first thing that we tried to do is, let's see, are these materials robust, okay, under sodiation? Okay, because for battery materials, we want the material to be resilient, okay, under constant bombardment of sodium, okay, because for charging and discharging, what you do is you intercalate the material with sodium, okay, that's during charging, and then during discharging, you let the sodium out of your material. So it's like your material is being under stress, right? And so what we want is that we want that material to stay in its current structural phase. Okay, since the material has two phases, 1H and 1P, so we want to see if by adding sodium, it won't transition to 1H, from 1H to 1P and vice versa. And this graph shows you or tells you that, okay, upon adding sodium, okay, the transition barrier becomes higher as you add more sodium. Okay, now the meaning of this energy barrier here is that the higher this barrier is, the more difficult is this material is to transition from 1H to 1P. That's the meaning of this transition energy barrier. So this graph tells us that VS2 is structurally robust and it's resilient under continuous charging and discharging processes. Okay, now in terms of metal binding, we also found out that this material, okay, in terms of sodium adsorption, is very stable. Okay, from this equation here, so you can calculate the binding energy by just simply using a simple expression. Okay, so you calculate the total energy of your VS2 with sodium, the total energy of just the 2D VS2 and the chemical potential of sodium, and then you subtract these two from your system, from the total system. And from this definition, the binding energy should be negative. The more negative the binding energy is, the more stable is the adsorption. And we found out that for this material, it's very stable. The adsorption is very stable. So around -2 eV, -1.8 eV for the two phases. That means these are good materials. Okay, and high specific energy capacity is expected. Okay, now in terms of diffusion, okay, we can also calculate. Okay, we can also calculate how sodium ions would migrate on this material. And using DFT, we found out that the migration barrier or diffusion barrier of sodium ions on the material is very low. That's less than 0.1 electron volts. Okay, that implies that the migration of sodium ions on these materials is very fast. Okay, and that would also mean that your material or your battery, if you use this material for sodium-ion batteries, would charge very fast. Okay, that's one of the potential implications of having this very low diffusion energy barrier for sodium ions. Okay, so that implies that this material, VS2 2D VS2, is a very good candidate for sodium-ion batteries. Okay, and actually, the good thing about this is these calculations inspired many experimentalists to actually synthesize the material. Okay, so there are many experimental researches that were done, okay, that utilized VS2 nanosheets or 2D versions of VS2. And they try to see if, okay, since the properties of these materials, as predicted, is very good for sodium-ion batteries, then let's try. And the results show that indeed VS2 are actually good. It's a good material for sodium-ion batteries. Okay, and another good news is that next year, a company in China would actually start using sodium-ion batteries in their vehicles. And the first batch of those vehicles are two-wheeled electric vehicles. Okay, and they will be utilizing sodium-ion batteries for the first time. Okay, of course, this is just an announcement. So they say possibly next year, this would be possibly the first EV cars that would have sodium-ion batteries. Okay. Now, another thing, okay, that I would like to share to you is that using DFT, you can also survey many 2D materials, okay, and try to see, okay, are these materials possibly good for sodium-ion batteries? What happens if I change, let's say, in this case, I change the transition metal? Okay, so these materials are what we call transition metal tellurides. Okay, so instead of sulfur, we utilize tellurium as our calvigen. And so you can replace the transition metal with many other metals and try to see their properties. Okay, and so what we did here was, okay, let's just probe these materials and see which are good for sodium-ion batteries and what possibly the reason is if they are not good for sodium-ion batteries. So we found out that for most materials, okay, the binding with sodium is very good, and also the corresponding diffusion energy barrier for sodium is also quite okay. It's less than 0.1 eV for all the materials. But the most important thing that we found out was that for these materials, okay, because you have different transition metals, right? So the corresponding charge distribution between the metal and the calvigen components would also vary. Okay, so take note that the electronegativity of your calvigen is higher than the transition metal. So it's obvious that electrons would transfer or would be shared unequally. Okay, so charge will transfer or will be more present on the tellurium side compared on the metal side. And if we change the transition metal from cobalt to scandium, it turned out that the corresponding charge transfer or charge redistribution becomes higher. Okay, so the trend is the charge transfer from metal to your tellurium is becoming higher and higher. And if you compare that to the corresponding sodium binding energy, that's also the case. The sodium binding energy also becomes more and more stable. Okay, so the idea here is, okay, maybe we can use this charge transfer phenomenon here to guide us, okay, in the design of the appropriate material for sodium-ion battery. So in the future, what we can do is, okay, let's search for a transition metal that would result to a higher charge transfer to the corresponding calvigen atom. Because from our results, we found that it could probably result to a very good binding of sodium to that material. Okay, so the important takeaway from this work is that the charge transfer between the metal and the calvigen could be tapped as a design parameter if you want to design an appropriate electrode for sodium-ion batteries. Okay, so now some takeaways, okay, from this talk. Okay, so quantum confinement effect, as I have discussed in this talk, that's okay, that's the reason for the plethora of new properties that you can see on a 2D material that are not present in their bulk counterpart. And so computational materials physics, okay, can aid us in the prediction and revelation of 2D materials properties, and could also aid us in the design of new 2D materials, okay, especially via DFT. And 2D materials, of course, so this is the main actor in this talk. Okay, so there are a wide range of applications of 2D materials. And one of the most important applications is in energy conversion and storage. Okay, so it turned out that 2D materials are very good candidates as new electrode materials for batteries. They are also good materials for water splitting, and very good materials for catalysis like hydrogen evolution reactions. So those are the good things about 2D materials. So it can revolutionize energy conversion and storage. Okay, so to answer the question, so this is the title of the talk. So 2D or not 2D, so I would say we go for 2D. Okay, and so before I end my talk, okay, let me just share to you Okay, so I'm a member of a research group in IMSP-UPLB. It's called the Materials Computations Research Group, or MATCOM. If you want to know more about our research group, then you can just scan this QR code here, okay, and browse through our page. Okay, so with that, thank you very much for your time and for your attention. And I think that's it. Thank you. Thank you again.
All right. Thank you so much po, Dr. Putungan, Professor Putungan, for the very enriching talk, to say the least. Ako po, if I could just like make a comment, it brought me back to my PhD year. So by the way, sir, like I worked on essentially metal sulfides and nitrides during grad school.
Okay.
I can very well relate to this talk because we actually studied, not really studied, I'm sorry, not really studied, but essentially looked at molybdenum sulfide as proxy for
Yeah.
essentially understanding active sites of hydrogen evolution catalysts, or those systems that
Nice.
actually break hydrogen bonds. So essentially splitting
Yeah.
a hydrogen molecule into hydride. So ayan, kaya para sabi ko, napaka-relatable naman ito. But then as we're waiting for questions from our audience members, so we have like about like 40 people dialing in between Zoom and YouTube. So bali sir, there's a couple of things that I really appreciated about this talk, and ang dami nating pwedeng i-unpack. Yung unang-una po, maraming salamat for taking your time to course our audience members through the process of yung DFT, no? Kasi I'm quite sure that a bunch of our folks out there must have heard the term DFT, in one form or another. Pero hindi lahat merong ganong klase ng kumbaga fundamental understanding kung ano ba talaga yung DFT, how systems are actually simplified into a model or a subset of variables that would still be a reasonable representation of a particular system na kaya pong itackle ng ating software. Ano po, no? So maraming salamat po dun, sir. So siguro po, mag-start muna ako with questions. Ako muna yung magtatanong.
Okay.
So sir, siguro po, sa Philippines, so marami po ba tayong mga groups that are practicing DFT calculations, for example, for research? And
yes, actually.
Yes, sir.
Yes, actually, there are many groups in the Philippines that are doing DFT calculations. I think one of the most active groups in the Philippines are in LaSalle.
Okay.
Yeah, so yeah, they're also doing DFT calculations, and I think there's a group also at NIP in UP Diliman.
Yep.
Yes. And I'm not sure yet, but I think there are also people doing DFT calculations somewhere in the south. Yeah. So yeah, it's an emerging tool, I think, for most physicists here in the Philippines.
Yep.
Yeah. So I think maybe in a few years from now, pwede na rin siyang maging parang yung normal way of doing material simulations in the future. Yeah, it's growing. It's a growing field in the Philippines.
Okay. And seriously, po, in relation to what you just said, like to build on that, ano po ba yung mga usual applications na ginagamitan ng mga Filipino DFT experts for research, lalo na sa Pilipinas? Ano bang areas nila ina-applyan?
Okay, so sa atin, mostly they apply it on materials. Yeah, so usually they try to predict properties of materials, especially for important applications. Yun nga, usually catalysis. Kasi yun nga, ang isa sa mga problems that we want to solve is how to replace fossil fuels. And I think ang pinaka ina-eye ng mga scientists is hydrogen as a replacement to fossil fuel. So we use hydrogen as an energy carrier. And so we can use DFT. Okay, we can use DFT to try to screen for materials that could be good catalyst for what's called hydrogen evolution reaction. So kasi hydrogen is not it's not present in large quantities naturally, right? So we need to produce it. And so in producing hydrogen, kailangan din yung ating mga makukuhang materials ay hindi katulad ng platinum. Kasi platinum is actually the best. It's the best catalyst for hydrogen evolution reaction, but it's very expensive in its noble metal. So if you're going to use it to mass produce hydrogen, then hydrogen will be very expensive. So you cannot do that. So that's why most people are trying to use DFT to predict new materials, new cheap materials that are also good for hydrogen evolution reaction. So I think that's one, usually for energy, conversion, storage, and catalysis. Okay, and a few, okay, I think a few of them are also doing calculations on semiconductors. Like you can also predict optoelectronic or photovoltaic properties of materials using DFT. Like, good pa yung material na to for solar cells or not? Can you tune the band gap or the bond structure in such a way that your semiconductor would be or would have a direct gap na bond structure? So things like that, like you can do doping, you can change the structure. Those are the things that DFT can help with, and particularly yun. So it can help with the design of the material for certain applications. So mostly I think doon nag-revolve yung paggamit ng DFT in the Philippines.
Okay. And siguro, sir, isa din na na-appreciate ko from yung first part ng talk mo, which I think is a very important teaching moment para po sa ating mga audience members, was yung slide mo talking about yung importance ng experimentation and then yung computational work, and then yung kumbaga yung sweet spot in between those two areas. So just for context, sir, I'm an experimentalist. I'm a chemist by training. I've done materials engineering, catalysis, hard X-ray sciences, and I have worked with DFT experts over a course of about 8 years po. So and I'm one of those who appreciate yung value ng DFT calculation. So siguro, sir, gusto ko lang po hingan kayo ng siguro if you could make comments further about yung importance of yung balance between experimentation and computation. If you could also speak about yung limitation ng quality ng work, if you're only working experimentally or if you're only working computationally, where is that fine balance?
Okay. Actually, computational physics, okay, its main use nung una siyang na-conceptualize was actually to supplement. Okay, so its purpose is to supplement experimental results. Okay, kasi of course, ang lagi namang arbiter ng ating mga discoveries ay experiments. Okay, so computations are used before to supplement experimental results. Now, ang isa siguro masasabi ko na so that's the balance. Okay, in terms of balance, dapat ang maganda talaga is that if you have an experimental results, it's also good to have a computational results to validate each other. And then meron ka pang mapropose na model for a certain phenomenon that you're studying. So that's the complete package. So you have experimental results, you also have models and computational results. Okay, now, in terms of, I would say, one main usefulness of computational physics, okay, ay doon sa mga situations or phenomenon na hindi tayo makapag-experiment. I think that's where I would say yung computational physics could be used as a sole source of results. Like for instance nga, another example pala is, for example, if you want to know the structure of materials in the Earth's core, kasi it turned out that scientists nowadays are finding out na, for example, iron ay basis yung structure niya dito sa ating crust, right? But it turned out na kapag sa loob pala ng Earth's core, ang kanyang structure is not anymore BCC, it's now hexagonal. So nagbabago na yung mga properties ng material under extreme temperature and pressure. And it turned out na meron din silang ibang mga properties. So, of course, those kinds of things ay sa ngayon hindi natin magagawa experimentally, right? It's very difficult to mimic yung temperature and pressure conditions sa isang lab. So now, currently, the only way that we can probe those properties ay through computational physics. So isa yon sa mga situations we're in, talagang computational lang yung pwede nating magawa. Okay, but of course, we hope that with the advent of new technologies, baka may makagawa na rin ng, let's say, equipment na pwedeng mag-mimic ng ganung environment sa lab, then that's better. Okay, but yes, so the idea is that for a good research output, okay, kailangan balance tayo. So meron tayong experimental results, then we supplement it with computational results, and we validate each other. So yun ang para sa best package talaga for an excellent research output.
Ayan. So ito po, kaya ko din tinanong to, sir, is that, like maganda din kasi may collaboration between experiment.
Yes, yeah, collaboration.
Yep. And siguro, sir, I would also just like to share appreciation of DFT experts like you. Kasi, for example, based on an experience, while I was still working for the one of the US's Department of Energy laboratories, was that when you were trying to innovate on a catalyst design, right? Nag-explore rin kami, sir, ano bang metals yung pwede namin ipalit? So sa halip na screen namin yung buong periodic table, we actually worked with a computational expert, and she identified, okay, these are actually more likely the metals that would work very similarly, if not better than the system that you have. So kaya ko po ito binabanggit sa ating audience members, yung pinakita po kanina ni Sir Darwin na tinetest niya, ano ba yung mga metals na pwede mong ipalit sa lithium? That's actually one very important value of computational physics.
Yes, yeah. Collaboration, I forgot to mention that. That's very important. Collaboration between experimentalist theorists and computational physicists. Yeah.
Yep.
Not to give the best research output. Yeah.
Yes. Yung pag-innovate kasi sometimes din kasi when you're working on projects, you don't have the luxury of time and you don't have the resources to put the entire periodic table in your material.
Yeah.
So sometimes you can identify yung kumbaga most likely candidates through computational scientists. So kaya ako, sir, I really enjoyed working with DFT experts like when I was still in academia and doing government research. But anyway, sir, meron tayong mga questions na pumapasok na. So I will start by reading yung question from Esona. So this is more, I think, career guidance type of question. So sabi niya po, hi sir, what are the most important skill sets to be learned to be a computational physicist if I were to start from zero? So little to no background knowledge.
Okay. Well, for me, I think the most important trait that one should have, una muna, is yung interest. So I think if you want to go into computational physics, then ito dapat yung interest mo talaga. Like, ang interest mo talaga is to construct, let's say, algorithms, to do modeling, to do simulations. With that, kapag may interest ka, magpa-follow na kasi lahat. Like, kung interesado ka talaga in computational physics, you'll find out later na, okay, parang you'll feel na madali lang palang mag-program, madali lang palang mag-algorithm, madali lang mag-model. But if you're not interested, like for instance, pumunta ka lang ng computational materials physics, but it's not really your interest, mafe-feel mo kasi yun na parang hindi siya madali. So for me, that's the first, I think first thing that one should possess, yung interest mo dapat. So you should be really interested in what you will do. Okay? And of course, after that, kailangan din medyo mag-start tayong mag-learn ng skill. Kasi ang skill naman natututunan yun, so it can be learned. So we should start learning how to use the computer. Of course, that's the most important thing. Somehow we should be a little well-versed paggamit ng computer, pag-program, like we can start simple programming. Usually in computational materials physics, yung mga softwares na ginagamit na, usually they were written in Fortran. So somehow it's an advantage if you know how to code in Fortran. But Fortran is a very old programming language, and I'm not sure if universities are still teaching it. Okay, kasi ngayon ang mga tinuturo na is yung high level or interpreted programming languages like Python. Okay, yung Fortran, I think kung aaralin mo siya, doon mo na lang siya matutunan. But it's good to know for that if you're going to academia, okay? Especially in computational physics. So, yun, I think it boils down to your interest and then passion. So, yun muna yung una. I think everything will follow kapag meron ka qualities na yun. Okay.
Ayan, alright. And then siguro sir, po, question lang din po for computational physicists like you. You mentioned something about programming, ano po. But if people won't, so it would does it suffice to say din po that if they just learn how to use the software, they don't necessarily have to code to perform DFT calculations, for example? I mean, lahat po ba ng computational physicists, do they have to code, or is it also like a matter of, merong mga established software out there and all they have to do is to learn how to use it and leverage your physics knowledge to interpret the data? Meron po ba yung ibang path?
Well, possible naman yun. It's possible actually for one to do computational works na medyo sabihin na natin you're not really very good at coding. There are instances or may mga software na parang click ka na lang and then that's it. May mga ganun naman na software. But usually kasi, those softwares are very expensive. Like for instance, Material Studio. I'm not sure if some of you have heard of that software. Material Studio is very good. It's a very good software because you can construct your material. Kunyari may minomodel kang material, you can just draw it there. Pag submit mo ng job to do DFT calculations, you just simply click a button. Pag tapos na yung calculation, you click a button, give you the results. May mga ganun na software, okay? But napakamahal ng mga ganung software. I think it's worth millions of pesos yata yung license. So hindi siya for countries like us. I mean, they cannot afford those kind of software. So maganda pa rin talaga na you have a knowledge of coding because there are certain things that you can do yourself na hindi mo kailangan bilhin. A corresponding software na yun, na kaya mo naman palang i-code, na madali lang pala, why buy an expensive software? So I think case-by-case basis siya. So pero pwede naman. So if you have the resource to buy those software na expensive, then go. Walang problema doon. That's okay. But if you think na, we don't have that resource to buy the software, we'll just code ourselves. Then good in yun because you can save money. And you're creating your own resources. So case-by-case basis siya. But to answer the question, it's possible. Yeah, but just a caution, in doing DFT calculations, dapat alam natin yung fundamental physics or chemistry ng ating ginagawa. Okay, because ang golden rule ng DFT is that garbage in equals garbage out. Meaning to say, if you don't know what you're doing and you just want to do DFT calculation, like, I'll do DFT calculation. Okay, I want to predict something, but you don't know what you're doing. Then most probably your results would also be garbage. I mean, pwedeng wala siyang kwenta if you don't know what you're inputting or what you're doing, what you're modeling. So yun ang good, I think that's one important advice. We should know the basics. So we should always refresh our physics and chemistry knowledge kapag nagmo-model tayo. Kasi importante yun. Para yung results natin ay accurate din, at the same time, may makukuha tayo, may extract tayo ng information. So that's one advice that I could give.
Actually, sir, nakakatawa kasi that was a question that I was intending to ask you for the benefit of our audience members. Ano po? Kasi, like all models will spit out all sorts of results. And it's also a question of when do you know if the model is giving you reliable results or when is it illogical. So si Sir Darwin, he actually pointed out like a very important aspect of practicing computational studies, which is you always have to have a solid command of the fundamentals. based din doon po sa experience namin, sometimes you would input structures of molecules, and once you get yung model na
Yeah.
yung structure na ibibigay ng model mo, sometimes it doesn't make sense. And so yung sinasabi ni sir is you have to have yung a strong chemical or physical intuition, no? Dapat consistent pa rin with
Yes. Yeah.
So, sir, thank you so much, kasi I think like this, it's, you know, like though ang ganda sir ng pagkaka-structure niyo ng inyong talk, kasi you ended up, you know, like dun sa application, but then ang ganda po nitong mga binabahagi niyo sir na kumbaga fair warning rin sa mga students, just because you learn how to use the model doesn't mean that you're gonna get all the right answers. So a good I think a good practice of computational scientists as well is that you always have to interrogate the results. Diba, sir? Ayan.
Yeah.
So, ayan, sir. So, siguro po, sir, if we have high school researchers po in the audience, no, and they would like to get started, you know, like when it comes to computational modeling, meron po ba, sir, mga fundamental resources that they can actually check out for them to at least kumbaga develop yung basic skill set?
Okay, I think nowadays somehow medyo madali nang makakuha ng resources, ano? Like for instance, even in YouTube, you can actually find videos na nag-tutorial sila ng simple concepts ng DFT, or yung tinatawag na, let's say, DFT for dummies or DFT for beginners. Yes, so marami na ngayon. So there are a lot of resources na yung iba nga talagang they produce very good videos. Napapanoorin mo na lang, and okay, ganun pala yung ginagawa. So yeah, the first thing is, yun, make use of the resources available online. Actually, if you search on Google, napakadami na pwede natin makuha ang resources. And if you're a passive, let's say, ang gusto mo nanonood ng video, so yun nga, there are now lots of videos in YouTube that you can search. And actually, there are institutions like the International Center for Theoretical Physics, yung sa ICTP in Italy. They upload, pag may workshop sila, they upload all the videos on YouTube, and pwede mo siyang panoorin whenever you want. So there are many other institutions that do that. So ang dami na talagang resources ngayon na pwedeng pagkuhanan ng information about, let's say, DFT or computational physics in general. For high school students, I think kasi ang DFT, kailangan mo muna ng background ng quantum mechanics. Okay, and I'm not sure if sa ating high school curriculum ay may quantum mechanics na. I'm not sure. So siguro sa high school, ang unang pwede sigurong matutunan nila or siguro aralin nila is simple modeling using, let's say, Python. Kasi yung Python, I think most ay familiar maybe sa Python. Kasi yun yung ginagamit ngayon even in producing games or something, ito ginagamit na yung Python. Meron sila mga packages doon for computational materials na I think ang purpose is to help you learn how to do simple codes. So yun muna siguro sa programming side muna. Tapos later on siguro kapag nagkaroon na sila ng courses on quantum mechanics, solid state physics, kasi kailangan talaga yon. That's the kumbaga baseline yung mga yon. So that's when they can now try to develop kumbaga yung programming nila na skill, pwede na nila ilagay yung natutunan nila sa quantum mechanics, solid state physics, so that they can start simple projects. So yun. So I think yun siguro yung for high school students. Siguro ano muna, develop the interest, and then read some papers, siguro educational papers on computational materials physics, and yun. And then take solid state and quantum mechanics later on. Importante yun if you really want to go to this field. Yun nga, sabi natin kanina, we need to have a solid background sa mga fields na yun.
Ayan, thank you, sir. And then, so siguro po, based on that answer, sir, ano po, more likely, if they would really like to siguro get their first taste of DFT calculation and its application and research more likely, sir, pag undergrad na sila, no, at nagtithesis. So,
Yes,
eto
yeah.
question ko sa inyo, sir, since you have a
Thesis.
research group in UPLB, yun po bang mga thesis students nyo are given the opportunity to also learn DFT at
Yes.
level?
So yung aming undergraduate students, their thesis are on DFT. So sa amin, sa research group namin, meron talaga silang training. So they'll be trained how to use DFT calculations. They will also be trained how to use supercomputers. Kasi ang DFT, especially if you're going to study large systems, you cannot just do that on a normal computer like laptop. Maybe taon yung aabutin mo to finish a certain calculation. So we also train them how to use a huge computers, yung mga high performance computing machines. So yun. So, and then after the training, that's when they will start to think. Okay, so ano bang gusto mong aralin? Like ano ba nag-i-interest sa'yo na direction ng research mo? Then we'll try to come up with a problem. And yun, okay, so let's use DFT for this problem and let's see kung ano yung makukuha natin. Na information or resource or properties. So yes, so sa lab namin, so yeah, you can learn DFT. So sa mga high school students na may balak, let's say mag-BS Applied Physics sa UPLB, you can try to consider our research group. Yeah, if you want to learn DFT calculations. Yes, and also, nga pala, yung group din namin, may mga students kami na sometimes, kasi may internship na component yung aming program. So we also send some of our students abroad, like Japan or in Taiwan. So that's where they can really learn more on DFT calculations. Kasi doon kasi talaga yung clusters, yung mga supercomputers. Kasi sa Philippines as well, we have core, okay? That's a good computing cluster also. Pero of course, sa Taiwan and Japan, doon yung malalaki talaga na supercomputer. They can really use that hands-on. They can even visit those labs. So medyo nakaka-inspire kapag nakakita mo talaga yung mga ginagamit. So yun. So that's also possible, yung mga internship abroad. You can learn more, you can meet new people. Yun. So yun, if you're interested.
Actually, for perspective, I have seen like one of those large, like those supercomputers that research institutions like yung mga nabanggit ni Sir ay meron, no? So for example, dun po kung saan ako nagtrabaho for the US Department of Energy, they were simulating the brain. So actually po, yung computer, yung supercomputer nila ay isang buong building. Literal na isang buong building. So, ganun na po yung kapasidad. So, maganda yung binanggit ni Sir na hindi ito yung software na install mo sa personal computer mo and then you can actually come up with results. So, and it's also good, Sir, that you mentioned that to a certain extent, we have some capabilities like in the Philippines. Now,
yes.
Core.
So actually, yes, I think lang kailangan siguro ng konti pang push or support from the government. Kasi yung core natin from ASTI to OST, that's actually could be a starting point para makagawa tayo ng similar infrastructure like sa Argonne Lab sa US or sa Japan and Taiwan. So yeah.
Ayun. Actually, Sir, doon ako sa Argonne nag-work. So
yeah, okay.
Yeah, and so essentially, Sir, kung meron po tayong mga undergrad level students dito sa audience who are intending to venture into research project na medyo DFT related or computationally oriented, how do they request access po dun sa core? If kung knowledgeable kayo, Sir, paano po ba kayo magre-request ng time?
Okay, so if you're a student, so ang requirement lang is that you write a letter. Okay? And then yung letter na yon is to be endorsed by the advisor. So, kailangan may research topic ka na nagagawin, tapos endorse yun ng advisor. And then, yung core, meron silang something like a Google form. Doon na lang talaga mag-a-apply. Then you just upload there your letter. And then you'll just wait, I think, 3 days or a week, from 3 days to a week para sa approval. As simple as that. Then they'll give you an account. Yung account, it's good for 3 months. Okay, so you'll have an access or you can access the machine for 3 months. Ngayon, kung hindi ka pa tapos, let's say you're still doing calculations, tapos na 3 months na, you can just renew it. So, ganun lang uli, may renewal form din sila. It's a separate application form. Renewal, you just submit it, then another 3 months. So, ganun yung ginagawa nila. So, parang you renew your account every 3 months hanggang matapos ka ng work. But the requirement is that, of course, first, kailangan may ginagawa ka talaga that needed that infrastructure. And meron kang advisor, of course. Yun yung dalawang requirement para maka-request ka ng account from core.
Ayan. So we would like to encourage our audience members to ask questions po that you may have. Pero yun sir, ako sobrang natawa ako sir dun sa talk ninyo kasi
Thank you.
It actually it covered yung entire spectrum ng computational physics, from fundamentals like how things are actually how studies are designed, all the way up to applications at na medyo sustainability related, sir. So pero siguro sir,
Thank you.
Since medyo wala tayong questions, baka sila na-overwhelm sila sa computational physics. Siguro sir, if we could ask for you to send messages of encouragement din sa mga guro at mga estudyante na siguro po may interest or medyo ngayon nagiging interesado na i-explore yung computational physics and DFT, for example. Baka po pwede nyo silang bigyan ng words of encouragement. Ano ba yung mga posibilidad? I know mention nyo na to kanina. Ano pa yung mga posibilidad para po sa Pilipinas? Saan pa ba natin to pwedeng gamitin?
Okay. Yeah. Yes. Okay. So for those who are interested in doing computational studies in the future, so I think this field is an emerging field in the Philippines. So I think that's one good thing about it. It's still emerging, so there are still lots of opportunities, okay, lots of things that you can study and lots of things that you can explore, okay. And so yun nga, another thing is that one of the problems that we will be facing in the future is yung energy problems, right? Isa yon sa mga pwedeng opportunities, like we can use calculations to predict yun nga, new materials, new processes that can help, okay, in alleviating the problems na yan, pagkawala ng fossil fuel in the future, anong alternative natin na fuel, isa yon sa mga pwedeng application ng DFT calculations. Okay, and then
okay, medyo na-interrupt yata yung internet connection ni Sir Darwin Putungan. Or is it me? Janet?
No, naputol talaga.
Naputol yung kay Sir.
Yes.
Actually po, ito, ang ganda nitong talk ni Sir. So sana po, itong webinar na to is actually recorded and will be uploaded sa ating YouTube channel. So, balikan niyo po yung mga binanggit ni Sir Putungan na applications of computational physics kasi ang ganda talaga nung pagkaka-design niya nung talk kasi meron talaga hanggang application. Sir, going back, yan, medyo naputol po kayo kanina.
I'm sorry, nawala yata.
No
nawala
problem.
internet connection.
That's okay. Ayun, sir,
Okay,
going back.
so yun. Okay, going back to the words of encouragement. So I would say, if you want to do something, don't think first if you can do it or you cannot do it. Just do it. So if you're really interested with computational materials physics, tapos meron kang doubt, ay baka hindi ko kaya to. You don't think about that. You just do it. So later on, dahil interest mo yan and you have the passion, you'll see na madali lang siya because you like what you are doing. So yun. I think that's for the words of encouragement. I think yun lang siguro.
So and actually, sir, maganda po yung binanggit nyo that it's an emerging area. So ibig sabihin, if some of you would venture into computational physics in the Philippines, you're gonna be one of the founding group ng Filipino scientists na mag-establish na sa Pilipinas. And this is actually something that I would also like to highlight. Kaya po mabilis din yung technology development and innovation pace sa ibang bansa. It's because they actually take advantage of data. So yun naman po ang dito, ang puhunan din sa computational physics, it's really data.
Mm-hmm.
Ayan. So ayun po.
Yes, another thing nga pala, yeah. Yung ano din pala, DFT, yung mga computational physicists that are using DFT, they're also now venturing to data science, like machine learning. So that's another emerging field that you can also go into. Like sa pag-discover ng materials, you can couple DFT with machine learning. That would make your predictions much faster. So yun, so if you're interested with that, like interested ka sa machine learning, interested ka sa materials, you can actually combine them. And who knows, maybe in the future, you'll be one of those computational scientists na magiging pioneer sa Pilipinas ng ganong field, right? Like machine learning plus DFT. So, yun, isa rin yun siguro sa mga possible na pwedeng explore ng ating mga young students.
And yun nga, sir, maganda yung banagit niyo, sir, na transferable yung skill. So, hindi ka mapapako lang sa isang area. Marami kang pwedeng ma-penetrate din na fields with yung skills na nakukuha mo from computational physics. So, ayan. Sir, ako po, unang-una nakakatawa po, to encounter researchers like you in the Philippines who are at the forefront of an emerging area. Kailangan po natin talaga ng mga kaparehas nyo po. And hopefully sa mga estudyante at saka sa mga guro who've dialed in sa Zoom at saka sa YouTube, I'm hoping that itong binahagi ni Sir Darwin will siguro plant yung seed ng inspiration para mag-explore kayo sa computational physics or yung computational chemistry, for example, kasi kailangan po yan. It's one of the advantages of First Nations po when it comes to technology and innovation. So with that, maraming salamat po, sir, sa pagsama po sa amin dito at sa pagbabahagi.
Thank you very much.
Research at saka ng inyo pong kumbaga career journey rin, no? And so with that, I would like to take this opportunity to present this certificate of appreciation. Nakikita niyo po ba ang screen ko?
Yes.
Is it on the right screen? Okay, I want to make sure. Okay, we'd like to, Filipino Science Hub would like to present this certificate of appreciation to Dr. Darwin Putungan of the Institute of Mathematical Sciences and Physics at the University of the Philippines, Los Baños, for delivering the webinar, 2D or not 2D? That is the question. Organized by the Filipino Science Hub and held via Zoom and YouTube Live on the 5th day of November 2022. Given this 5th day of November 2022, signed by yours truly and Mr. JP Onya, Head and Vice and Chief Technology Officer of Filipino Science Hub and Filipino Science Hub Research University. Ayan. So baka po merong gustong humabol sa inyo ng question. Meron po ba? Mukha, sir, ito po. Again, this is like the final installment of our Physics month webinar series, po. And isa po sa mga rason kung bakit natin to ginagawa isa po sa mga bagay kung bakit po natin ito ginagawa is to kumbaga spread din po yung word about yung mga local physics experts po natin sa Philippines, to make it known to the broader community kung ano ba yung mga ginagawa. Kasi there's a lot of exciting activities and projects going on na kumbaga ang namumuno po or nangunguna ay mga kababayan po nating Pilipino. So I'm hoping po that like if you are interested in learning more about what's going on at the Institute of Mathematical Sciences and Physics, si Sir Darwin po, he shared yung contact information kanina using the QR code. So po, bisitahin niyo po yung mga websites na there's a lot of exciting things na nangyayari po. And then by the way, sinabi nga po ni Professor Edita Jose, aking pinakamamahal na math professor, pasimula pa lang po ito ng aming collaboration, marami pa po itong kasunod. And actually, yung isa po naming follow-up project after this is a math bridging program. So ang goal naman po namin doon is to help, kumbaga, enhance rin yung mastery ng ating mga high school teachers when it comes to teaching yung mga essentials ng math and also like preparing yung students pagdating ng kolehiyo. Kasi di po itong K-12 medyo na-shock yung system natin. So meron tayong ganyang project early 2023. So again, this is just the beginning of a pipeline of projects between Filipino Science Hub and the Institute of Mathematical Sciences and Physics. Isama kita sa spotlight, ma'am. Ayan. So, ayun po. So, at this point, Sir Darwin, maraming salamat. I personally enjoyed the talk kasi it brought back a lot of memories. Nasa industry na ako ngayon, so I don't.
Thank you very much.
I don't get to work with DFT experts anymore. Nandun na po ako sa medyo business side. But, ang ganda po nung talk ninyo. And so at this point, baka po pwede kami maka-request ng group photo, no? Sa mga kasamahan nating nasa Zoom para po meron naman tayong mga screenshots po. Ayan. And then may nagtanong, how to affiliate with PhilSciHub. Early next year, we're going to be opening up Filipino Science Hub for membership. Marami po tayong mga projects na nakalinya. Ayan. Baka po pwede naman kami maka-request na buksan niyo po ang inyong camera para makita natin ang inyong mga nagagwapuhan at nagagandahang mga mukha. Ayan. By the way, we're also joined by Dr. Janice Abrilla, who is who's based in upstate New York in the US. She's also one of the members of the core leadership team of Filipino Science Hub. Jack, say hi to our audience members.
Hello! Ang babata ng mga audience natin.
Oo, mga students sila yun. So, ayan.
Hopefully madaming ma-encourage na magtuloy sa computational.
Oo. And you know what? Ito, babagit ko lang din. Kung meron kayong research areas na interested kayong gawin sa Pilipinas as walang gamit, an opportunity for you to experience that would be computational physics, no? Kasi you can learn the fundamentals, you can make models, and then later on in grad school, kung gusto maging experimentalist after that, magagawa nyo. Anyways, count po ako na tatlo. 1, 2, 3. There you go. One more. Para po merong option ang mga tao. In case hindi nyo magustuhan. Alright. Bilang po uli ako. 1, 2, 3. Ayan. So, muli, maraming salamat po sa pagsama ninyo sa amin. Ma'am Edith, maraming salamat po. This has been like a very fun opportunity to work with IMSP. Again, the beginning of a pipeline of projects. So, magkikita-kita po tayo ulit soon.
Thank you very much po.
Ayan.
Kuya Jeff, may post test tayo, di ba?
Ayan, meron tayong poses. Wag muna po kayong aalis. Actually, yan, meron po tayong poses.
Tayo.
Yes, ito po ay Google form. Nandito na po ang poses at nandito rin po ang request form para po sa inyong certificate of attendance. Ayan. So make sure lang po that you input yung tamang spelling po ng inyong information kasi yun pong certificates are automatically generated. So sabi nga ni Sir kanina sa computational chemistry, garbage in, garbage out. Misspelled names, yun din po ang makukuha nyo, pabalik. Ayan po. So natawa sila. So be mindful po dun sa spell check. Ayan. So ayun po, muli maraming salamat po. Sir Darwin, maraming salamat po uli. Ma'am Edith, Zeus, our intern from UST, joined us today, and then Janice. We hope that everyone enjoys their weekend. Kita-kits po ulit tayo sa susunod po na schedule ng webinar ng Filipino Science Hub. And if you're interested in some of our future events, make sure to follow us on Facebook and also yung official website po namin, din po kami nagpo-post ng aming mga events. Ayan, ay saktong-saktong matatapos tayong 5 minutes before 12 noon. So hindi po namin may invade ang inyong lunchtime. Yan. Maraming salamat po uli and take care everyone. Salamat po.
Thank you.
Salamat po. Ma'am, kita-kits sa Pinas. Kita-kits sa Pinas. Dadalaw po ako sa LD.
Wow, yes, of course.
Yung tuna belly nyo, ma'am. Bye. Thanks everyone. Bye.